Well, good morning. Have a little something different today rather than HP RF test gear. I have this Tektronix TDS754D scope. Now, this is one of the 4 1 gigahertz scopes that I now have. It's a little bit of a long story to that. I wanted to get a 1 gigahertz scope because some of the gear that I've got here for measuring rise time of pulse modulation, you need a 1 gigahertz scope to check that the rise time is correct. So I've been waiting to see and get a 1 gigahertz scope, and I haven't been able to find one. And then, a couple of weeks ago, a bunch of them all became available. And so I bought, originally I bought a LaCroix LC574AL from an auction. A hard drive manufacturer down in California was shutting down a facility. So I bought this 1 gigahertz 4 gigasample a second scope from them. It turns out the manual says that to get 1 gigahertz you need to bond the channels together, and you need this particular adapter. It turns out that the manual was wrong with regards to the adapter, and the adapter that you actually need is completely unobtainium. I spent several weeks trying to find one. I contacted the LaCroix user group. No one seems to have the adapter. There was a guy on EEV blog that built his own, and it sort of seemed to work, but I didn't want to build my own adapter because I wanted to get something that was going to give me the guaranteed rides time that the manufacturer had put in. So I thought, well, I'll go get another scope, and I've been on the lookout for some other scopes, and then up came another auction, and in that auction there was a Tektronix TDS754C, which is a 1 gigahertz scope, and HP Infinium 54845A, which is a 1.5, I think, gigahertz scope. Now, I really wanted the Infinium scope, but the way you got to bid on these things, I ended up actually winning both scopes. And so I was like, okay, well now I have 3 1 gigahertz scopes. A little while I was waiting for those to arrive, they cancelled the auction and said, no, not getting anything. I was like, well, that's sort of a bit of a bummer. But right after they cancelled, up on eBay came this TDS754D. So I was like, great, well, I'll buy this. Now, it turns out that they didn't cancel the entire auction lot that I won. They cancelled one item and got confused. So now I'm a proud owner of 4 different 1 gigahertz oscilloscopes. Now, if you've been listening on, you've seen that I've said TDS754D, yet I'm referring to 1 gigahertz oscilloscopes, and this is only a 500 megahertz 2 gigasample scope. Well, it turns out that these TDSs were actually built with the same boards as the 1 gigahertz scopes, and so with a little bit of modification you can actually upgrade these to do 1 gigahertz. And so this set of video is going to be about me going through this process of getting this guy running and then upgrading him to 1 gigahertz. Now, I'm actually going to end up selling this guy back on eBay to recoup some of my money, because I've got the Infinium scope, and I should get that next week and be able to go through the process. Now, it doesn't boot, already know that, so there should be a repair video come out of that. Anyway, to get onto this scope here, I'm not a huge user of Tektronix gear. I haven't used a lot of it. It's been a long time since I used a Tektronix scope. In fact, the last one that I used at work was a little lunchbox model 2-channel 50 megahertz scope. So I really don't know a lot about this, and so all I'm going to be able to tell you is what I've learned from the research and looking at the unit. Now, these are great units, and they come from an era where there's actually a cathode ray tube, CRT, in here behind this screen. And what Teartronics was doing was, rather than have the CRT go and be color and have all of this capability and expense, they married the CRT with an LCD shutter at the front to go and give you the color. Now the problem was with a color tube you have convergence issues, so getting things nice and sharp and that was a problem. So what they could do is put an LCD filter, red, green, blue sort of filter at the front here, and turn them on appropriately as they were scanning the various parts of the display, so they could get a nice sharp monochrome display but still get a color resolution. So let's turn the scope on and have a look at that. Now a lot of people complain about the time that takes modern scopes to boot, and let me just turn my Rigol on at the same time. I have a TDS754D. I quite like it. It's a lovely little scope. You know, it's a 50 megahertz, 1 gigasample scope. It has 4 inputs, and I have the protocol triggering and analysis option for it. So it makes it a nice little bench scope to do some probing when I don't need to bring out my logic analyzer. So the Rigol has actually already finished booting, so these guys really take a while to get up there. And the Rigol scopes, as people keep saying, are not super fast in that boot process. So here we go. We've got the scope actually booted up here, and one of the reasons that I bought this was that you can see that it has some options here: 13, 1F, HD, 2M, 2F. Now the 1F means that it has the floppy drive in it. The HD means that it actually also carries an internal hard drive. It's about a 2.1 gigabyte internal hard drive. The 2F is the advanced math functions on it, so it can do DSP, it can do FFTs and things like that. And then the 13 I'm blanking on right now, but it's I think it's like a fairly standard option for this. Let me just take a quick look at the manual and get back to you. Okay, so the 1.3 is the RS-232 Centronics printer interfaces that they have at the back. And then the 2M is the 8 megabit acquisition length, which enables, what is it, 4 megabit or 8 megabit samples on a single channel. So that's what the sample, that's what the options are in here. Let me grab my coffee out of the road. So the scope's actually pretty simple to run. You know, you have 4 input channels here. You have vertical and horizontal control, trigger control, and you can, you know, if I drop a signal in, you know, we'll get the signal up there, and if I hit auto set, you know, the system will go away and work out how best to get that signal. Now, one of the things that you probably notice is the DPO here, and this is this digital phosphor oscilloscope. And so it's a feature on here that's designed to make the oscilloscope sort of try and act like the original analog scopes. And one of the big things that the analog scopes would give you is this persistence aspect in the display, because as you would scan the electron beam across the phosphor, it would take some time to actually fade, and so you could see glitches, you could see little delays or changes of things, because you would see that information fading on the display. So DPO is sort of designed to try and simulate that. So what I have here is I have a 50 megahertz 0 dBm signal, and you know, if I go in and turn on my AM my AM modulation, you'll see it come up. Now if we scale in there, you know, you'll see that it's got these little jumps, and the reason that it's got that is that this guy here does a thing called equivalent time sampling, and so it will try and get you a faster equivalent or a sample rate. So I can go into the acquisition menu and I can turn real-time on only. And so now what you're seeing is we're now sampling at 2 gigasamples per second. Now the equivalent time basically assumes that the signal is going to stay steady, and so I can sample once here and then I can sample just next to it but a little later, and effectively over a period of time I've created, as long as the signal is truly repetitive, I've gotten much greater samples for my signal. So it's actually a pretty good option, but it turns it on a lot by default, and I haven't read the manual and worked out how to turn that off. So here we have, you know, my AM signal. You can see that it's bouncing around like you would expect. And now if I turn DPO on, you now see that it's got this persistence value. And so you can see the heat map showing where signals are going. And so where it's gone red in the middle, you can see that there's more of the signal. And this is this sort of simulated delay or decode. So if I, fade that the CRT gives you. So if I turn this up to 50%, you'll see that, you know, I'm getting 50% of the signal, and it's all changed there. What I can do is, because these are digital, I can actually change the persistence, where you couldn't do that on an analog display. So if I turn on infinite persistence and then change my modulation back to 25%, you'll see that there was the change as the modulation changed gave me different colors based on the amount of signal path that has gone through that, and I can keep this persistence thing and see the difference in my signal. So DPO is actually pretty cool in that sort of sense, and you can turn it on and off really quickly on the 745Ds. I've never used one, but reading about them, the A and C series, apparently the processors aren't anywhere near as powerful, and so that turn on, turn off is quite challenging. So that's a quick intro to sort of some of the cool aspects of this system. What I want to do now is go in and let's run the self-test and see what's going on there. Okay, so now I'm ready to actually run the self-test. So to do that, I'm going to go Shift Utility, and then have a look at the error log, and we've got a nice clear error log. You can actually go clear these error logs. So that's what I did. Plugged in the GPIB card and then the adapter, and then you can issue it an errlog, ERRLOG space clear, and clear the log. So now that we've got the log clear, what I can see is just events that are related to what I'm doing here. So let's go in and select, with dialog there, the diagnostics error. I want to do all of the tests. I'm going to do them all, and I'm going to execute them, select all, and I'm going to execute them. Let me remove that signal, and then I'm going to do it once, and I'm going to confirm to run. And so what I'll do is we'll take this bit of the video and then speed it up super fast and see what the result of the test is. Okay, so now what we can see here is that there is actually a failure. Let me get find a little pointer so that I'm not poking the screen. What we can see here is that it passes everything except the acquisition test. Now, if I go and clear this menu and then go back to Shift Utility and then to the error log, we can see that we now got an error. Now that error isn't particularly useful from inside this error log here, but what I can do is I can get that error to come up through the GPIB, and we can get more information about that. So let's go take a look at that error. Okay, so we're going to record a little video here of my desktop, and see how it goes. Let's get ready to start. Okay, and we're going to go in 3, 2, 1. Okay, well, here I go. I have the connection expert for my GPIB stuff open. And sorry about the audio levels. I have a microphone that I bought that's a wired microphone for the desktop. I really think I need to invest in a microphone a wireless microphone for the video camera, and that way I can just keep recording audio on the video camera and get a constant level. Anyway, here is the Tektronix scope. We're plugged in, and if I do an IDN, we'll see that we get that the Tektronix comes in there. So what I can do now is I can do an log :first, which tells it to go get me the first entry. So if we do that, what we'll see here is that this morning at 8:30, when I ran the diagnostic, we had a failure in the acquisition memory at this address, and the address is 0x730020. What it was expecting was this piece of data, 101, and what it saw was 6161. Now, if you look at the errors that are occurring here, it appears that the first 4 bits, because we're always adding a 6, seem to have been just continually set. So to me, this tells me that there's a problem in the SRAM, or possibly the SRAM controller for the board. And I went out and I've asked on the forums if anyone's run into this and what that error address is. But I don't get a lot of I haven't got a lot of information on that. So I'm hoping that somebody will be able to help me find out where that address is. Because what they'll have when we go and have a look at the acquisition board is, for each channel they will have a bunch of SRAM chips, and so what the channel will be one of those chips will be bad, or possibly the controller might be bad, but it's probably more likely that one of the little SRAM chips itself has failed, and it's failed in only one of the acquisition boards, because it's saying it was testing digital B. So I'm assuming that the acquisition memory is like A, B, C, D, and so it'll be one of the channels that this is actually failed on. So while we go have a look at that information, let's go back to the scope and have a look at the actual board and see where this SRAM is, and then take a quick look at the area that we're going to update to make this a 754D. So now I've taken a little better look at that error. Let's take the unit apart and have a look at the acquisition board. So we'll turn the board off, the unit off here, and we'll go in and we'll unplug the back of it, and then swing it around so that we can see what's going on. And so this is the rear of the unit, and you can see this rear cover is held on by these 4 bolts here. I'm going to take this rear cover off, and then this whole panel should just slide off. So let's go do that, and then we'll come back and we'll actually have a look at the boards. So again, okay, so what we see here is the inside. This is the main processor board. You can see the enclosure for the CRT. The big honking fan that's in here. A bunch of ASICs that are around. This little switch up the corner here, you'll see referred to a lot. This switch enables you to write protect these non-volatile RAM chips that are here. This guy here, that's 1250Y, it's actually the same, this is the same chip that was in my 3458A. They have roughly have a 10-year lifespan. Now how they're actually built is inside the actual package is a little lithium chemical battery. It's a bunch of stuff. There's like lithium and then 2 or 3 other things in it. I can't remember right now. But that battery provides the power for this non-volatile RAM, and they expect about a 10-year lifespan. So if we have a look here, the date code on this is 9924, so the 24th week of 99. 10 years, so 2009, we're in 2016, so about half again past their design lifespan. So at some point, these things are going to die, and then you'll lose that NVRAM and stuff. This one actually here with the timekeeper also integrates a real-time clock inside that integrated circuit there. So if we flip the board over, what we're actually interested in terms of the repair is this acquisition board here. Now, there's some writing on the board, so I don't know if somebody's already had this board out and played with it, or if that was writing during the test. And so if we zoom in a little bit, you should be able to see that, you know, during assembly they may have written on the board, but we'll take I'll have to take a closer look at that. A little bit of gunk there. So let's zoom back out, and this is the memory. And so you can see that we have the acquisition channels here, and then this is the SRAM that's associated with each of the acquisition channels. So one of these things will be acquisition. There will be the digital B that it was testing, and then one of these individual SRAMs will have failed, and so they're all look like they're all little through-hole SRAM. Let me put my glasses on and take a little better look. Then, but they're very tiny pitch through-hole. But I should be able to identify which of these ones is actually which of these ones is actually going to fail, and then be able to fix that. Now, I wonder if this is interesting. Over here, you can see that they had on the board what clearly was meant to be a can, a shielding of some format, and then they didn't bother shielding it. So I wonder if that was what was going on there when they did that. So now I talked about the upgrade. The upgrade is actually pretty easy. There is, let me see if we can find it without needing to go do a bunch of research, because I looked at the article just fairly briefly. And so there should be 4 little surface mount resistors that will show the upgrade. I can't find them. I don't remember if they're on the processor board or on the acquisition board. Okay, let me go take a quick check. Okay, so I went and had a look and found where the resistors are. And you can see that they're up here, and this is these little resistors feed into this ASIC here. And if we go in and look, let me zoom in, and we'll get right in, and it'll take a second while it stops bouncing around, and then we get the macro in. You can see that there are 4 little resistors, and they're all little 0-ohm resistors. So they've been used as jumpers, and these 4 jumpers control what the acquisition board thinks it is, and the acquisition board then tells the processor board, hey, I'm a 784, I'm a 754, and so on. J. Diddy B from EEV blog, I think, was the guy that published this, and so I'll link to that below. But basically, this is where you would go to change this. Now, what he did is he started playing around with these jumpers and discovered that he could get the scope to return and say, hey, I'm a 784, a 1 gigahertz scope. But then when he went and looked at the rise time, he was not getting the bandwidth. And the reason that he wasn't getting bandwidth is that the Tektronix guys clearly worked out, well, somebody's going to go in and maybe modify that, or they thought, what's going to happen is, I can plug a signal in, and if I have too much bandwidth on the acquisition, I'll notice that I can actually read more of the signal, and I may never need to upgrade. So let's zoom back out, and let's go have a look at how they fixed that issue, or how they solved it. So what you can see here, if you have a look on the board, you should be able to see these differential pairs, and they're coming out of each of the acquisition boards that are under this cover here, and they're connected to the B and C's at the front. And so if we just zoom in a little bit more, so that we start getting, seeing the double pair, what we can see is you can see this little capacitor right here, and then another one just over here. And what they're doing, in fact, let's zoom right in and let it resolve. Oh, let me just move it. You can see these capacitors are sitting right across the differential pair, and they're being used to limit the bandwidth that comes out. So when you make the change to that resistors, you can go in and remove these capacitors, and you will then start getting the full bandwidth, because those capacitors are not populated in a 784, which is the 1 gigahertz scope. What you will need to do, though, is run the field adjust software, and so you need a special PC, or you need a PC with an ISA slot and a specific GPIB card to run that. So I haven't got that yet. So my first step, and let's zoom back out, my first step with this scope here is going to be, as I said, to look at these SRAM chips here and try and find the one that's dodgy, and then replace that so that I can actually pass the acquisition test. So in the next video, we'll go through, hopefully I'll have found by then which of these is actually being reported, and then we'll go in and have a look at taking this board out so we can flip it over and remove the chip and then replace it with an equivalent part. Hope you found this part of part 1 interesting, and I look forward to catching you in the rest of it.